Welcome to week 4. My name is Ludwig Jourdain and I'm an assistant professor at the Department of Biotechnology of TU Delft. In week 4, we are mainly going to talk about feedstock for biotechnological processes. In this lecture, we will first talk about how to translate the information from previous weeks into an integrated biotechnological process. As we have seen before, a biotechnological process is composed of different stages, each of which contains specific unit operations. From the choice of feedstock to the upstream processing of that feedstock, which includes all conditions and actions that are necessary to prepare it for the next step and conversion. This conversion can be fermentation, like in our case with PDO, but in reality, enzymatic, thermal, or chemical conversion processes are also used. After fermentation, the product is concentrated and purified in what we call downstream processing, and its specifications are adjusted to match those desired by the market. Finally, for optimizing process sustainability, a process engineer must recycle energy and mass flows, and the use of auxiliary streams is critical. Industrial processes are set up to sell products and earn money, of course, and there are also costs involved. Operational expenditures are related to the use of materials and energy, such as feedstock and auxiliaries. OPEX are also associated with waste and emissions that arise when feedstock are not fully converted into final product or recycled. Capital expenditures relate to equipment investments. And the main objective in the design of an integrated process is to balance the operational and capital expenditures of all the process steps, maximizing the margin that is earned after taxes have been paid. Because there is often a trade-off between CapEx and OPEX, optimization is not straightforward. What we would like to have is one simple recipe with ingredients that are always needed to design all unit operations in the process. The capital expenditure of a facility depends strongly on the type of product that is made. Typically, industrial biotechnology processes have an investment of 100 to 250 million US dollars. But it depends on the sort of product, how this investment is distributed between upstream, fermentation, and downstream costs. In pharmaceutical processes, the product purity is of extreme importance, and 80% of the capex can be spent on downstream processing. In bulk processing, for instance, for second-generation biofuels, on the other hand, up to 80% of capex may be needed for upstream processing and fermentation. Operational expenditures are also influenced by the product type. In this overview of biotechnological products, the cost price of the product is related to the production volume or the product concentration in the reactor. You see that the more diluted a component is, the higher the costs are. Most of the costs are actually the separation of water from a process. When designing a facility, the process engineer must quantitatively evaluate the following. What are the specifications of the product streams? How much should we produce and from which feedstock? And what is the equipment capacity and its mode of operation? Weeks 2 and 3 on fermentation and downstream processing discussed the specs, the scale, and the how. Week 5 will talk about conceptual process design more in depth, together with techno-economic and sustainability assessment. And the main focus of week 4 is on feedstock. As mentioned earlier, it is useful to have design recipes ingredients that work for multiple unit operations. And the 5 main ingredients are as followed. Firstly, setting up mass balances over flows entering and leaving unit operations. And secondly, understanding the distribution of components over the different phases. Thirdly, characterizing mass transfer and hydrodynamics. For example, to find out whether these process flows can actually be contacted in such a device from physical constraints such as pressure drops and flow resistance. And fourthly, dimensioning equipment to allow flows to remain in each unit operation sufficiently long to allow the process to progress to the desired extent. And finally, fifthly, setting up energy balances. Examples of how to use some of these ingredients have been given while designing downstream processes in week 3 and will be further used in week 5. An important technical, economical, and sustainable aspects of biotechnological processes is the feedstock used. Fermentation feedstock can be categorized in 6 generations. Generation 0 dates back thousands of years, with first evidence of fermented drinks from rice, honey, and grapes, using yeast dating as far back as 11,000 years BC. Generation 1 is based on sugar and starch, the most widely used feedstock in industrial biotech processes. Generation 2 corresponds to lignocellulosic biomass with some industrial facilities running, while Generation 3 relies on algae-based phototrophic processes. Generation 4 enables a circular economy and can be divided in 2 main types of bioprocesses, where 4G alpha captures and utilizes the off-gas CO2 from generation 1 and 2 fermentation, such as product yield on substrate is improved and net CO2 emission reduced, while 4G beta corresponds to gas and synthetic gas fermentations. Valorizations of organic waste such as food waste or municipal solid waste to value-added products corresponds to generation 4 as well, which allows resource circularity. Generation 5 is a newest generation and relies on direct renewable electricity input for microbial conversion. How else do the 6 generations differ? Here, generations do not reflect a sequence in time per se, but rather reflect their impacts on key environmental aspects, namely the net CO2 emission of the overall bioprocess, as well as the land use and impact on biodiversity, as you can see here. The rest of week 4 will discuss each generation as well as the integration opportunities towards sustainable bioprocesses. Thank you for your attention and see you at the next lecture.